Hello, so I'm Arthur Gretton of the Gatsby Computational Neuroscience Unit, and I'll be talking about a relative goodness of fit test for models with latent variables. So this is joint work with Hishiro Kanagawa, Witawa Chishkutum, Lester Maki, and Kenji Fukumitsu. So just to set the scene, what do we mean when we talk about a test of goodness of fit? So I'm going to give an illustration. This is the city of Chicago, which is broken up into regions. And perhaps we're interested in modeling crime in Chicago. So each of the dots on this map represents a robbery that took place in Chicago in 2016. So now let's say that somebody has given us a model of the crime. In this case, it's a mixture of two Gaussians. And they're going to ask us, is this a good model? Well, it turns out that in real world scenarios, the question, is this a good model, always has an easy answer. Which is that all models are wrong. And so given that all models are wrong in complex scenarios, it's helpful then to consider a better conditioned question that one might ask. So let's now say that we have two wrong models, but one might end up being more useful to us than another. Okay, so we have models P and Q. We have a reference sample x, I through 1 to n, from a distribution R. And the goal in this case is to determine which of model P or Q is the better one. So in this case, we've got a mixture of 2 components, a mixture of 10 components. One might suppose that the mixture of 10 components is the better of the 2, but we want to make this formal and to find a way of statistically verifying that one model is significantly better than another. Okay. Another point to keep in mind is that if you're a Bayesian and you're making a model of a system, then many models have latent structure. And so here is an illustration. This is a graphical model representation of hierarchical latent Dirichlet analysis with a nested Chinese restaurant process prior. I'm putting this up here not to go over all of the details, but just to show you that many Bayesian models is effectively like iceberg models. So you have an observation variable, but a great deal of latent structure underpinning that observation. And so a useful test of relative performance must be able to operate for models when you've got this complex latent structure. All right. So this gives all of the ingredients needed to describe the title. We're interested in a relative goodness of fit test. So both models are wrong, but we want to know which of the two is closer to the target data for models with latent variables. So we're interested in the kinds of Bayesian models that people are using in practice, which often have very complex latent structure associated with them. Now, to test goodness of fit, we need a test statistic, and our test statistic is going to be a kernel-Stein discrepancy. This is going to be derived from an integral probability metric, which is called the maximum mean discrepancy. And that's a discrepancy one might use if one is comparing models simply on the basis of samples from these models. I'm going to then modify this to compare not one sample with another sample, but a sample with a model which you use in closed form. And this is able to take advantage then of the model structure that we know, so of the model of the equations we have for that model. I'm then going to construct a relative test where I've got 2 kernel-Stein discrepancies, one for a first model, one for a second model. So I want to know whether one model is significantly better than the other. And finally, I'll describe how to use that relative hypothesis test in the event where I've got latent variables. And so that's going to actually end up being an additional source of quite considerable complexity. All right. So I'll start by introducing the kernel-Stein discrepancy. I've got a model P. I've got samples xi, I going 1 through n from Q. We know that all models are wrong, so we know that P and Q don't agree. And we want a measure of discrepancy between model P and data Q. So in this case, data Q are photographs of dogs, and model P are drawings of dogs. So they're not perfect, but hopefully they're not too far. So let's begin by introducing the notion of an integral probability metric. So this is a measure of discrepancy between distributions P and Q, which is obtained by finding a well-behaved function which maximizes the difference in expectation under Q and P. So here we see a well-behaved function which has large positive amplitude around the blue points, large negative amplitude around the red. All right. Now the function has to be well-behaved because then it gives a hierarchy of similarity between models P and Q. So in this case, we say that Q and P are closer together. The discrepancy in expectations is smaller, and it's smaller here than here because we've used a smooth class of well-behaved functions to distinguish the distributions. These functions are called the witness functions. All right. So how do we now define our class of well-behaved functions? Well, the class of functions you use determines the integral probability metric that you get. We're going to use reproducing kernel Hilbert spaces as our witness class. So the next two slides are a crash course in reproducing kernel Hilbert spaces. These functions are actually quite simple. They're just functions which are linear combinations of features, but there may be an infinitely large dictionary of features. So in this case, I've got my features, phi1, phi2, and so on. I take a linear combination of those features with coefficients f1, f2, and so on, and that gives me my function. The norm of the function is just the sum of the squared coefficients, as you might expect. You can see that these features get less smooth and their amplitudes drop as we go down the dictionary. So this is a property of these functions. Now, writing functions of infinitely many features can be a problem because you need infinitely many coefficients, but it so happens that you can get around this problem using the kernel trick, which I'll describe now. So here is my function of infinitely many features, and I've plotted it in green here. But let's imagine now that the coefficients that define these functions can be written as a weighted sum of coefficients of features, of coefficients alpha, multiplied by features evaluated at some xi. Okay, so these are the features at some xi. I take a weighted sum of those features, and that gives me my vector, my infinitely long vector of coefficients. Well, if that's the case, and if we know the dot products between the features of xi and the features of x in closed form, that's this kernel function, then I can write my f of x as a finite sum, where I only need to remember the coefficients alpha and the locations xi at which I'm evaluating my features. So in this illustration, my kernel function, my dot product between features, is a Gaussian. And so I've got a sum of Gaussian bumps centered at xi, weighted by coefficients alpha I. Okay, so in the event that I can write my f as a sum, then my function can be written using only finitely many coefficients and finitely many xi's. All right. So now let's use the unit ball in a reproducing kernel Hilbert space, so the unit ball in the previous class of functions, as my set of witness functions for my integral probability metric. So here I've got EPF minus EQF. And you can see that I've got a smooth function which has positive amplitude where there's more red mass and negative amplitude where there's more blue mass. So this is the case. I've just got two Gaussians with different means but the same variance. All right. Now, if I've got a rich enough dictionary of features, so this is called a characteristic reproducing kernel Hilbert space, then this is a metric on probability distributions. It's 0 if and only if P and Q agree. But there are other good functions, witness class functions that you might consider. All right. Now, an issue arises when you have a model P, and you may not be able to evaluate the expectation under that model of F in closed form. All right. A solution might be to sample from that model, but that ignores the model structure, so there might be a better approach. Now, an approach might be to get rid of the expectation of F by applying what we call the Langevin-Stein operator to my witness functions of my integral probability metric. So here's a Langevin-Stein operator in one dimension. It's 1 on P ddx of F times P. All right. Now, if I apply this to a function F, then the expectation under P of the Langevin-Stein operator applied to F is going to be 0 subject to boundary conditions. It's quite easy just intuitively to see why that is. If I take the expectation under P of this expression, then I get effectively the integral of the derivative of F times P, which is going to be 0 as long as the F times P vanishes at the boundary. All right. So this is a function of the P and the derivative of F times P. So this combination of P and its derivatives is going to crop up many times in this talk. So let's now compute the integral probability metric where we've applied the Stein operator to our witness function. Okay, so the Langevin-Stein operator is being applied to our witness function. now we try to compute the integral probability metric for our reproducing kernel Hilbert space class. This expectation is 0 because we've applied the Langevin-Stein operator, and we're left with the largest function that maximizes the expectation under Q, our sample, of the Langevin-Stein operator under P, our model of G. Okay, so here is our example with our two Gaussians with different means. Here is our G function, which maximizes this. And what you can see is that it has large amplitude where the data disagree with our model. And then as the mean of Q approaches the mean of P, the amplitude of G gets smaller. And if P and Q agree, it's going to be the 0 function. Here's our example of the city of Chicago, where we've got our crimes and our model. In this case, the grayscale is the witness function in this case, illustrating the mismatch or where the largest mismatch occurs between the model and the data. And you can see that this happens in Lake Chicago because there are no crimes in the lake, there are no pirates in Chicago, but our mixture model is still placing mass in the lake. All right, now we need to be able to compute our test statistic for the kernel-Stein discrepancy. And thanks to the kernel trick, this is going to be possible. So it turns out that the kernel-Stein discrepancy, when I square it, has a closed form solution, which is the expectation under x and x prime drawn from the model. So these are independent draws from the model of this HP of x and x prime. So this is called the kernel of a U statistic, not to be confused with the kernel of a reproducing kernel Hilbert space. This U statistic kernel is formed by a number of terms. Now, one term is going to be the derivative of our model P divided by P. So recall from the Langevin-Stein discrepancy, you've got this derivative of P on P. And we're also going to get these terms here, SPK2, SPK1, and trace of K12, which are going to be functions of the derivative of the kernel. So K1 is the derivative of the kernel with respect to its first argument, K2, derivative of kernel with respect to its second argument. And the derivative of the kernels arise because you've got the derivative of the function from the Langevin-Stein discrepancy, but this function then gets the kernel trick applied to it. And so everything gets expressed in terms of kernels. So this is very satisfying. We can compute this. A very important point to keep in mind with the kernel-Stein discrepancy is that even if you only know P up to normalization, you can still compute this because the normalizer cancels. So I've got derivative of P on P, normalizer cancels, and I compute this even if I only know P up to normalization, which for complicated models will very often be the case. Now, when will this be 0? Only when P and Q agree? Well, as long as my feature space is rich enough, so we're going to call this a C0 universal kernel, and subject to a condition on the derivative log P on Q being satisfied, then this will be 0. The KSD will be 0 only if P and Q agree. So it's going to be able to find any difference between the model and the data Q. We can also define the kernel-Stein discrepancy on discrete variables. So let's say that our discrete variables are alphabets of size L, and each word contains D letters. I can define the kernel-Stein discrepancy, and you'll notice that visually this looks very much the same as the Stein discrepancy on the previous slide. A difference is that this SP quantity, so derivative of P on P, now gets replaced by a difference operator of P on P. So this difference operator takes the difference of P, where I increment one of my letters to the next letter in the alphabet, minus P evaluated at the current word. And I do the same for my kernel. So I apply the reverse difference operator to my kernel on X and X prime with respect to the first entry. So I also need a discrete kernel. The kernel we'll use in our experiments is going to be the exponential of the Hamming distance between words X and X prime. Okay, now because of the form of our kernel-Stein discrepancy in population, the empirical estimate is a U statistic. So if I've got samples Xi and Xj from Q, I get this double sum where I is not equal to J of HP of Xi and Xj. Now, because all models are wrong, because P and Q disagree, the empirical statistic, this U statistic, will have an asymptotically normal distribution around its mean. It's a non-degenerate U statistic with this variance here. So here's a numerical simulation illustrating that the empirical kernel-Stein discrepancy is in fact, in practice, quite well approximated by a Gaussian around the population kernel-Stein discrepancy. Now remember our goal. Our goal is to do relative goodness of fit testing. So now we have two rival models, P and Q. So this is one artist trying to draw dogs. This is a second artist trying to draw dogs. And we want to know which of these two is closer to the reference distribution of photographs of dogs. So let's say we have a kernel-Stein discrepancy between model P and R, a kernel-Stein discrepancy between Q and R. We have samples from R, we have distinct models, and then we want a hypothesis test. So the null hypothesis in this case is that the kernel-Stein discrepancy for P is less than Q, so P is better than Q, closer to the null, so closer to R, and the alternative is P is worse than Q in this instance. So P is worse than R. Okay, so HL naught is P is as good or better than Q, and H1 is Q is better. Now, because we know that P is asymptotically normally distributed around its mean, and Q likewise, these have a joint asymptotic normal distribution, illustrated here, which makes a relative test very straightforward. So I just take the difference, and this difference is going to be asymptotically normally distributed around its mean, and the variance is going to be given by these sigmas, which are given by the joint asymptotically normal distribution. So it's very straightforward, thanks to this normality, to get a statistical hypothesis test with the null hypothesis that P minus Q is less than 0. So that's straightforward. So now recall a source of additional complexity, which is that the models that we care about in our tests are going to be, in most interesting cases, latent variable models. So these are models with a very complex unobserved latent structure, and only a small amount of these models gets observed. Okay, so now let's illustrate this. So P of x is the integral of P of x given z pz dz. Q of x is integral of Q of x given w pw dw. Now, very often we will not be able to do these integrals in closed form. So if our models are sufficiently complicated, as the one in the previous slide, we don't have closed form expressions for these marginal distributions, Px and Q of x, right? Now, recall the multidimensional Langevin-Stein operator. So this is the multivariate case of the univariate example I gave earlier, which is defined as the dot product of f, which is vector valued and derivative of p on p, plus the dot product of this and f. Okay. Now, this is going to be, the expectation of this will be 0 if I take the expectation of this under P, but this requires the marginal distribution of x in closed form. And as I've said, we don't have it, okay, for many interesting models. So what do we do? Okay, so here is the result that we need when we're computing the kernel-Stein discrepancy, this SP of x, which you'll remember is the derivative of P on P. We don't have P of x, but what we can find using some very simple algebra is that this can be expressed equivalently as the expectation of the posterior of z given x of the s for the likelihood, the s for the P of x given z. And we do have P of x given z in closed form. So we have derivative of P of x given z on P of x given z, and we take the expectation over that, over the posterior of z given x, and that gives us our quantity here. So how do we get this approximately? Well, we want the expectation of z given each of our samples xi of sp of the sample xi given z. We get the posterior z given xi using Markov chain Monte Carlo. So conditioned on xi, we sample z given that xi. We take m such samples after a burn-in period t to ensure that we hit the stationary distribution, and we use those m samples to approximate the distribution of z given xi, and that's our approximate sp. Based on that approximate sp, we can approximate the kernel of the U statistic. So if we had an exact if we had an exact sp, I should say, then we would have the following exact U statistic. So this is the standard kernel-Stein discrepancy. We replace the kernel of that U statistic with an approximate kernel, h bar p. H bar p uses s bar p, which is the s that we get by using Markov chain Monte Carlo to sample the z's for each of the xi's. Okay, so we have an approximate U statistic. It's a noisy version of our population U statistic here, evaluated at xi and xj. Now, we might be concerned at the asymptotics of this approximate U statistic, but we can show that the approximate U statistic is still asymptotically normal with a variance expression here. And so as a result of this, if I compute a difference in a difference in approximate U statistics, KSDP minus KSDQ, then this is also asymptotically normal. And thankfully, that means that our statistical test becomes straightforward, just as it was when we had models without latent variables. Now, here we do need a little bit of care, because we're computing the statistic using Markov chain Monte Carlo, so we need to be sure that we've done sufficient burn-in to remove the bias. There's also a moment constraint, but we don't need to worry about that too much. All right. And in practice, we estimate the variance of our asymptotically normal approximate U statistic using the jackknife. So that's how we compute that. All right. Let's look at an experiment now. So the experiment I'm going to address is the case where our data are archive articles from stat theory, and our models are LDA models trained on articles in different categories. So there will be a poor match, okay? So in this case, P is trained on math PR, math probability theory, and Q is trained on stat methodology. So one might imagine that P is closer to R than Q, okay? So here are our results for this. So this is the rejection rate of the null. So in this case, we want to reject the null, and rejecting the null in this example amounts to saying that P is a closer model than Q, all right? And what you can see is that as you see more and more reference samples, so that's as we go up the x-axis here, we become more and more confident in rejecting the null and concluding that math PR is closer to R than Q, all right? These parameters here are the parameters we've used. So we've got a vocabulary of size roughly 100,000, and we're using documents of 100 words long. So we truncate the words in the document, and we're using a kernel as described here. All right. So what's very reassuring about this is that if we compare against the maximum mean discrepancy, which is a relative test where rather than using the model structure, as we do for the Stein test, we just sample from the model. So we sample from P, sample from Q, and we do a relative MMD test rather than a relative Stein test. This is much less powerful in this example. So you can see that our rejection rate, even up to 500 samples, remains much lower than the Stein test does. So the Stein test, by using model structure, is able to successfully distinguish P and Q. So that concludes the talk. I refer to two papers here, a kernel test of goodness of fit and a kernel Stein test for comparing latent variable models. So this one just it uses the basic kernel Stein discrepancy. This test here describes a relative test where we've got models with latent variables. So I'd like to thank the Gatsby Charitable Foundation for the funding, and I'm happy to take questions by email. Yeah, so thanks.